welcome to today's webinar on atmosphere applications in Wikio. So what we will go through today is an expert session or an expert webinar which will detail the atmospheric applications that you can develop with Copernicus data and information in the Wikio DS. So we have several experts here today for you to explain how to work with atmospheric data and how to develop applications. We have from ECMWF several scientists. We have Antje Innes, a senior scientist of the Copernicus Atmosphere Monitoring Service, as well as Mark Parrington, also a senior scientist at the Copernicus Atmosphere Monitoring Service. And then Julia Wageman, who works at EUMETSAT and MEO, who will give more information about the use of the Jupyter notebooks. And then Amin El Amrani and myself are from Wikio user support, and we will talk to you about the Wikio DS itself. So what's specifically on the agenda today? We will start with an introduction to the Wikio DS, what it can do, what it offers, by Antje. Then Amin will take over and give a presentation on the IT infrastructure and the pricing for the use of the Wikio DS. I will then also give a very brief overview of which data you can find in the Wikio data catalog. And then we will move on to the demonstration parts of the day. Mark Parrington will discuss the unique features of Wikio for air pollution monitoring. And Julia Wageman will give a live demonstration on atmospheric applications in Wikio. We will have time for questions and answers at the end of the session, where just to explain to you how that works. So during the webinar, you can ask any of your questions in the chat window. You will see. And it's changed again. So you can ask any questions. Either our experts will be answering in the chat, but we will also take the questions at the end and go through them in a live Q&A for about 15 minutes, depending on the time that we have. If you have any more questions afterwards, please don't hesitate to reach out to us on our web portal, on our Twitter at WikioDS, or our service desk email support@wikio.eu. And then I will now give the floor to Antje to present the Wikio DS. Good morning.
Good morning, and thanks a lot. Yeah, welcome to this webinar on atmosphere applications. I'm Antje Innes. I work at ECMWF in the CAMS team on the assimilation of Sentinel data. And I will give you a short overview of what Wikio is for those of you who have not followed a webinar before. Wikio is one of the 5 Copernicus DSs that was launched by the European Commission to facilitate and standardize data access to Copernicus data. So who is involved in this? Wikio was developed jointly by EUMETSAT, ECMWF, Mercator Ocean, and has now also been joined by the European Environment Agency, so that we can provide fast and easy access to Copernicus data. All of this was implemented by industry through procurement. So what does Wikio contain? It is a single data access point to all the Copernicus data, and that means data from the services such as CAMS and also the Sentinels. For this, Wikio uses cloud computing and provides a lot of tools that allows you to handle the data. And we also have a very strong emphasis on user development and management. So we have a high level of user support, and we run training courses and webinars like this one. And then finally, it can also serve as a marketplace if you develop any products based on the Copernicus data. So what is unique about WEkEO? Well, one thing is that the DIAS partners are also the producers of the data. So by joining WEkEO, you have first-hand contact to the data producers and can benefit from their expertise. Also, most of the data that is on WEkEO is not a copy, but makes use of WEkEO's distributed infrastructure to link the data from various centers together. That means you always have the most up-to-date data and you don't need to rely on copies and perhaps have out-of-date data. Also, the data stay where they are and you can work with them there. So you don't need a lot of disk space to download data. And finally, the distributed nature of WEkEO also means that it could easily be extended to new external partners. So we have the potential to grow. And then, as I already said, there's a strong focus on user development with training courses and webinars, and then also expert user support, frequently asked questions, guides, videos, and so on. So this was a quick recap of what WEkEO was, and now I will show some examples of what WEkEO contains and what we can do with it. And I will focus in this part on the CUMS global reanalysis. This is a self-consistent long data set that covers 18 years from 2003 to 2020 and gives you atmospheric composition data. So you have a lot of tropospheric data, for example, tropospheric ozone, NO2, CO, aerosols, and you also have stratospheric ozone. And this data set can be used to study past events, to build climatologies, or look at anomalies if you want to assess how unusual certain events were. And in this talk, I will use it to look at stratospheric ozone and the ozone layer, with a focus on the Antarctic ozone hole and then also the Arctic ozone layer. I guess most of you will know the ozone hole story. It was discovered in the 1980s, and then it became clear quite quickly that it was caused by man-made chemicals, the chlorofluorocarbons, or CFCs, and the international community then came together and adopted the Montreal Protocol in 1987 to phase out these chemicals. And as a result, the ozone layer is now slowly recovering. But because of the very long lifetime of the CFCs, this is a very slow process. And even though models suggest the ozone layer will recover eventually, this is not going to happen until the second half of this century, very likely. And this image you can see here in the colors is an example from last year, from October 2020, showing the Antarctic ozone hole. And you can see in the blue colors the really, really low values down to 100 Dobson units over the Antarctic. And we're used to seeing ozone holes over the Antarctic, but we don't really see something similar happening in the Northern Hemisphere. And the reason for this is that the meteorological conditions are very different in the Northern Hemisphere. The stratosphere, that part of the atmosphere where the ozone, most of the ozone resides, is a lot more perturbed in the Northern Hemisphere and the Southern Hemisphere. And we don't get the same conditions that allow the chemical reactions to happen to the same extent. But this was very different in the previous year. Where am I now? There. Oh, okay, I've got it now. This is what I want to show at the end now of my talk. Normally, the values in the Northern Hemisphere, as I said, are a lot higher than in the Southern Hemisphere. But in some years, we find conditions that allow a much stronger ozone depletion than usually happens. And this is shown here in a plot that shows that combines C3S and CUMS data. So this is another advantage that WEkEO brings. You can combine data from the various services. And it shows a time series of the March ozone north of 63 degrees. So we start here going back to 1979, because we can use the era 5 C3S data for the earlier years, and then we use the CUMS reanalysis here for the later years. And I've also superimposed some other data sets for comparison. And here we have ozone values. And what you can see is that the values are quite high in the earlier years, and then you get this decline in the 1990s as the CFCs destroy more and more ozone in the ozone layer, and then you have higher values later on. But what really stands out is that there are 3 years that are very, very different with very low values. And the lowest of them all was 2020. And the reason for this was that the polar stratospheric temperatures in 2020 in the spring were exceptionally low, and the polar vortex was exceptionally strong. So this polar vortex is a region of very strong winds in the stratosphere that surrounds the pole and separates the polar regions from the mid-latitudes. And normally this region is quite perturbed in the northern hemisphere, and you get mixing between the extratropics and the polar regions, so that low ozone values don't really happen. But in 2020, it was very strong, as you can see here at the bottom plots, which show you the zonal wind in the stratosphere for December, January, February, March, and April. And you have these strong red colors showing you the strength of the vortex. So it was a lot stronger than climatology. And then here at the top, in the middle plots, you see the corresponding temperatures, and you see it was very, very cold. And this then allowed the chemical reactions, and we came to these very, very low ozone values that were a lot lower than climatology. So the next slide. And one nice thing about the CUMS data is that it's not just total column data, but it is a 3-dimensional data set. So you can also look at the vertical distribution of ozone in the atmosphere. And that is shown here. We have here a cross-section through the ozone layer. So we have height on the y-axis from the top of the atmosphere down to the surface. And then we go from the equator along 70 degrees east via the North Pole and back to the equator. And you can see the red colors show you the ozone layer with the high values. But then as you come to the North Pole, you see this blue area where you have very, very low values, where the ozone depletion happened. And the profiles on the right show comparison with ozone sound data at New-Ålesund in Spitsbergen. The top are ozone profiles, and the bottom are temperature profiles. And the red lines show you the year 2020, and the other line shows you the climatology from the CUMS reanalysis, and you can see how different last spring was. So this is just one example of what you can do with CUMS data. And I just want to finish off by just pointing out again, if you have any questions, please contact the Wikio user support. There's a 2-tier system. The level 1 support is operated by a dedicated user support team. And if they can't deal with certain questions, they can escalate it. And then you get the level 2 user support, where senior experts from the partners will deal with your questions. And that's the end of my talk. Thank you very much.
Thank you very much, Antje. So we'll move on with a short introduction by Amin about the Wikio pricing and infrastructure. Good morning, Amin. Hi.
Good morning. My name is Amin Al-Amrani, and I am part of the support team of Wikio. And I'm going to do a brief presentation of the IT infrastructure of Wikio, which consists of 2 main services. On the one hand, we have the Jupyter environment, and on the other hand, we have the virtual machine. So For those of you who are familiar with Wikio, you can see that we have a brand new website now. It is online since a while ago, but this new website comes with a more intuitive design. As you can see, there's a documentation section that has been revisited, and so do not hesitate to take a look at this new documentation section and the FAQ before sending us a message, because you might find your answer there. And let's start with the Jupyter notebook. So all you have to do to have access to the Jupyter notebook is to register to Wikio. I already have an account, of course, so I can sign in here. And once you have signed in, you can click on the dashboard button here. And then you click on Jupyter Hub. So I've already opened it here. And what is Jupyter Hub? So the Jupyter Notebook or Jupyter Hub is an open source web app that you can use to create and share documents that contain live code, equations, visualizations, and text. And this is the welcome page of the Wikio environment, so to speak. And so you have access to whether a classic Python interpreter, a terminal prompt that allows you to browse through your Jupyter environment. So your environment is a kind of small virtual machine environment after all. You can also create documents from scratch if you click here, and you can use this Jupyter notebook that you have created, whether to use the cells. You have code cells, or you can have also markdown cells, or you can put some augmented text or raw text. So I can show you quickly. I'm using this from scratch. If I put the markdown here, click the play button, we can have this kind of titles. We can also use the Python cell. If I copy some code here, so I make sure that the cell is a code 1, and if I click the play button, we can have a plot of data. So this is why the Jupyter environment is a very useful teaching tool, as this code is associated to text and images. And I would advise you to read one of the typical Jupyter notebooks that we have, that you can access through the folder public WEkEO HDA. So as you can see, this is one of the many introductory documents that we have. It contains images, code, instructions. You can see that this is a code cell. This is exactly if you were on a Python interpreter. If you click the play button, it will play the code. And the outcomes and results of the code running are actually displayed on the document itself. So I do not have time to go through the whole document, but I would really advise you to read it, because in this document you can copy the HDA request, the description of your request. The code is encapsulated in the Python functions used here, will allow you to target a certain number of products of interest, and these products will be downloaded using other functions in the function in the following code cells later in the documents. So getting familiar with these documents will make you very comfortable with the Jupyter environment in a matter of hours. And you should know also that these documents can be exported to a PDF. If you want to have a PDF copy of the document as it is shown here, or if you want to keep only the Python code, it is also possible to export the document to pure Python code that can be used elsewhere by running the code on a virtual machine, for example. And this brings us to the virtual machines. Some of you might ask, why would we need a virtual machine environment? Isn't the Jupyter environment enough? But the thing is, the Jupyter environment has limits. It's not meant for long and heavy processing. The storage capacity is limited. The CPU and the memory are also limited. So it is ideal for testing and mingling with data, but it's not meant for heavier processing. So if you want to perform some heavy processing, consider switching to one of our virtual machines. So Wikio has a virtual machine resource offer. And to request a virtual machine, you should go to the dashboard again and click the upgrade plan button here at the end of the page. Here you can choose a configuration that corresponds to your needs and fill in the rest of the form. So here you can choose the plan size. We'll talk about this later. You can give us some information about the intended use of the platform, the Copernicus data that you will need. And you can see at the end of the page, we have this small table with the pricing that corresponds to each plan size. So we have a better table here.
Amin, we're running a little bit later. Could you quickly go over the pricing, and then so we move on to the demonstrations?
Okay, so I go a bit quicker. So we have this pricing section, as I was saying. Each plan corresponds to a certain pricing. And if you have any questions about how to get the virtual machine, you send us a message to the support@wekeo.eu, and we'll answer your question. So I am sorry about the time, and so I'll give it over to Anne-Catherine.
Thank you, Amin. I'll just briefly, before we start with the demonstrations, give a short introduction to the data catalog, but more will come from during the demonstrations about the atmospheric applications. So the Wikio gathers all of the data from the Copernicus program, which means the Copernicus Marine Environment Monitoring Service, Climate Change Service, Atmosphere Monitoring Service, and Land Monitoring Service, as well as the Sentinel, Copernicus Sentinel data, Sentinel 1, 2, 3, 5P, and soon as well Sentinel-6. And so today, just to briefly give the background, in the Marine Environment Monitoring Service, you find all kinds of information related to the blue ocean, so physical parameters of the sea, the green ocean, biophysical, biochemical parameters in the oceans, and then the white ocean sea ice, both for the European seas and globally. In the Land Monitoring Service, we also talk about the European land cover, land use at a very detailed level, plus also at a global level, whereby you find also vegetation parameters, but at a lower resolution, so that you can monitor vegetation globally. And then finally, the Sentinel data, which might be of interest to you as well, can be found on the Wikio DS for you to play around with. And as Amin has already shown, the data sets are available in a catalog in a viewer on the Wikio DS. And this is as a brief background to the data catalog on the Wikio DS. And I will now leave the floor to Mark Parrington to talk about the focus of today, the atmospheric applications and the data. Hello?
Okay, hello everyone. Hi, Katrine, can you hear me okay?
Yes.
Okay, great, thanks. Okay, yep, hello everybody. So I'm going to give an overview of the products from the Copernicus Atmosphere Monitoring Service that are available in Wikio to fill in the gap of those that Anne Katrine just showed. So I need to use my mouse here. So yeah, so as we've already seen about the other Copernicus services and the Sentinel data available on Wikio. At ECMWF, we run the Copernicus Atmosphere Monitoring Service, of course, but also the Climate Change Service, and that data is available on Wikio. But I'm only going to focus on the CAMS data this morning. Okay, so we have 4 main categories of data sets. These are regional European products, global products, some supplementary products, and emissions products. And I will go through each of these just to give you an idea of what's available. I should point out from the beginning that the inclusion and addition of CAMS data sets onto Wikio is not yet complete. It's still a work in progress, but we're slowly getting there. And the data that are not available on Wikio can be accessed by the CAMS Atmosphere Data Store, which I'll continue to refer to as ADS, which has a web interface and an API for access. And I'll point out where the data that currently isn't available on Wikio is and how you can access it. So we'll start with the European regional products. So these are essentially air quality analyses and 4-day forecasts. They are provided from a suite and ensemble of 9 individual models, which use consistent emissions and lateral boundary conditions, which are taken from the CAMS global production system. They have a 10-kilometer spatial resolution and provide hourly information on air pollutants, for example, ozone, N.8, particulate matter pollen from the surface up to about, I think, up to 5,000 meters. And just to point out, the multi-model ensemble is very helpful because it combines all of the individual models into a median state and actually performs often better than the individual models themselves. In terms of the global products, so the headline product is the CAMS global reanalysis of atmospheric composition that Antje already presented earlier in this session. And so I won't spend too much time on that, but basically it provides a self-consistent data set with a spatial resolution of about 80 kilometers from 2003 to 2020. Antje showed very nicely the applications for the ozone layer and ozone hole monitoring, but also there's a whole range of other atmospheric composition species and products that are available through the reanalysis. Other global products that are not yet currently available on Wikio, but can be accessed through the Atmosphere Data Store, are the operational analyses and 5-day forecasts of global atmospheric composition. So this is our main product that we produce in CAMS at ECMWF. And so this is really the global air quality atmospheric composition with a spatial resolution of about 40 kilometers. And there is another reanalysis product that we have available currently via ADS, which is of global greenhouse gases. So this is covering the same periods, using the same system, but is for carbon dioxide, methane, and I think nitrous oxide, and possibly carbon monoxide, but certainly CO2 and methane as the main greenhouse gases. If we move on to the supplementary products, one of the main ones of these is solar radiation time series. So the products are available for cloudy and clear sky conditions. For clear sky conditions, it does at the global scale, but at cloudy conditions, it is only available for the field of view of the Meteosat satellite, which is a geostationary satellite covering Europe and Africa. And all the data are available from the 1st of February 2004 to the present. Other supplementary products that we have are available via ADS, and these are mainly global radiative forcings, so the radiative impact of different pollutants on atmospheric radiation fields. And then finally, the emissions products. So those data that are currently available on Wikio are our global emissions inventories. So these are data sets that provide estimated emissions from emission sources, including both anthropogenic and natural. So anthropogenic could be road traffic, energy production, agriculture. There's a range of sectors that we provide anthropogenic information for. And natural sources are things like biogenic emissions from vegetation, from soils, from the oceans, and those are the data available. We also provide, we also have a product which is greenhouse gas fluxes, and this is based on in situ observation networks. And this covers different time periods depending on the greenhouse gas you're interested in. So for carbon dioxide, it goes back to 1979. Methane covers from 1990 up till 2019, and nitrous oxide from the mid-90s up to 2018. Emissions are an essential part of what we do in CAMS in terms of our forecasts. And so we do have other data sets available. These are not yet added to Wikio. So we have daily estimates, in fact hourly estimates of global wildfire emissions based on satellite observations of active fires. These are provided through our global fire assimilation system. And this data is not currently even available on ADS, but is available through our older CAMS data catalog, and access can be granted through contact with our user support. And in addition to the global emissions inventories, we have emissions inventories which are regional for the European domain, which also covers a little bit of North Africa and the Middle East. So there's various channels of support for CAMS products, in addition to the Wikio channels that have already been shown. So particularly for the products that are available through Atmosphere Data Store, if you need more information on the background of how those are produced, more information can be found through the CAMS website. There's a link here to the Atmosphere Data Store. And our user support channels and Twitter feed are also listed there. And then, of course, there's the Wikio channels. So with that, I'm finished. I'm happy to take any questions.
Thank you, Mark. So I believe then we go over to the demonstration by Julia. Good morning.
Good morning, and also hello from my side. I just start sharing my screen. I hope this works. Okay, yes, so good morning also from my side. As Anne-Kathrin already said, I will showcase you how you can work with the Jupyter Lab environment, which Amine presented, and I will focus specifically on the CAMS global reanalysis data set Antje presented, and I will specifically focus on the ozone hole anomaly that appeared last year over the Arctic. I want to just let you know that you already, if you log in, so Amine showed you how you can sign in and how you can go and access the Jupyter Hub platform. And so if you open the Jupyter Hub platform on Wikio, you will see most likely an interface like this. And I just want to let you know that the notebooks we prepared for today's session is already available on Wikio. So if you go to the public folder, you see a list of different folders, and under atmosphere, and then the folder which with the day or date today, the 27th of May 2021. This is the Wikio webinar. You see or you find the content which we will go through today. There was also a question on how to access the data directly, and also Amine invited you to have a look to the HDA API. So this is the API, how you can retrieve data directly from from Wikio, and I will go through a notebook showcasing you how you can retrieve the data we use for the training, and so you can also retrieve the data yourself, and then you can continue with the training, because the data is not available in this public folder, but there is the notebook with the number 10 showcases you how you can retrieve the data in order to proceed to the notebook number 11. For the training today, I already prepared the same copy of the notebooks in my workspace, just to save some time and to be able to showcase you everything. And then you can have a look for yourself and in a self-paced manner after the webinar. So there are 3 notebooks available. And I invite you to start with the first one with 00 index. This basically just gives you an information on what this webinar is about, and also what this course or what notebooks are available as part of this webinar. And then basically I will go through the notebook number 10, which guides you through the different steps that are required in order to access the data. And I will also showcase you how you can prepare a data descriptor file for the specific data for CAMS global reanalysis data, but also for other data sets you might be interested in. And so, as I said at the beginning, how Amine already introduced you. So Jupyter Notebooks is a combination of text and markdown information, but also code cells. And this makes it so powerful because yes, we can create very nice step-by-step guides in order to guide you through the different aspects in order to retrieve data. So how Jupyter Notebooks works is that if you click on a cell, and this is now a cell that contains code, it is activated, and if a cell is activated, then you see a blue ribbon on the side here. And you can execute a cell, as Amine showed you, with this arrow in the navigation bar on top, or you can also use your keyboard, and you can use Shift and Enter, and then also the cell is executed. And we start with loading some libraries we need for Python, and we also have a set of helper functions which help us to retrieve data from the HDA API. If you are interested in how these functions look like and also what these functions are doing, you can have a look to the HDA_API_functions notebook. And if we open this notebook, you see a set of functions that basically make it easier for you to work with the HDA API. And so there is quite a few functions available, but in the end, it is easier also just to apply the functions and to use the approach what we showcase you here. And so with this command here, all the functions that are available here. So it is just one function after the other. We load all the functions, and then they are available also in this notebook. And so we execute again this code cell. And the first step is basically to go to Wikio and to browse through the data. And so you can go to the Wikio website, you can go to the data, and then you can so basically this is so you can go to the plus, and then you can here browse through the data. And so in our case, we are, for example, interested in the CAMS data. we can click on here, and then we can see, for example, CAMS Global Reanalysis. We can get here more information about a CAMS Global Reanalysis, about some specific metadata. And if we add them directly to the map, then we are in a position where we can also either download the data or, oh, I have to log in again. 1 moment. So I log in quickly. And then we are in a position that we can select our bounding box of interest, the date range we want to have, we be interested in retrieving data, and also specific variables we are interested in. And if you look below, so there are quite a few variables available. So if we select all the parameters, you see at the end either request data, and this is the request if you want to if you're not on the Jupyter Lab, if you just want to download the data, or you can go to the show API request. And this API request is important because with this request you can build up your data descriptor JSON file, which is needed for the HDA API. And so I invite you to have a look through the notebook. We gave you here a step-by-step guide on how to browse for the data, and also how you can then get your API request. And the interface here gives you then also a button where you can copy directly the information of the request. And this is what we also did for the data for the training today. And the API, this request, we saved in a JSON file, and you can open this JSON file. This is also part of the training or the training files we make you available. You can open this file, and you see here a JSON file with all the information we basically also just selected. So we have the area, which is global, which is selected. We have date, which is from the 1st of March 2020 to the 31st of March 2020. We have here a variable, and we only select the total column ozone because this is the variable of interest for the example. We specified 2 time steps, but there are also other time steps available. So, but just for training purposes, we selected the time 0 UTC and at noon at 12 UTC. And at the end, we also said that the format we're interested in is netcdf. But and so with this data descriptor file, we can go on and retrieve the data from the HDA API. And so the first step is basically we define the dataset ID, which you can also retrieve on the website and as part of the API request. And then you can generate an API key, which is part or which is a combined key consisting of your username and password, which you need in order to log into Wikio. And so you can here specify your username and password, and then if you execute here this function, then a specific unique key for your password and username combination is created. And then we have a set of different steps that are needed in order to initialize the HDA API, and also to request an access token, and also to accept terms and conditions. And the different steps are required because with each step, what is done is basically we set up or we create a dictionary of all the information we need for the HDA API in order to retrieve the data. And so you see here that we get an information that we accepted the terms and conditions. We have the data set ID, and we also have a download directory path and also the API key. And so with each of the subsequent steps, our dictionary is extended with the necessary information. This is an important step here, because here we load the data descriptor file, which I just showed you. And this is the file that contains the meat, so basically the data we want to retrieve. We load it, and with the data, once we loaded the data descriptor file, we can then initiate the request. And in this step, our request is getting a job ID assigned. And so then the query is submitted, and then until the status is completed, we also get regular updates. And then we can see what files have been found in the HDA API. And we see here basically one file has been created, and the last step, or the one step, is then to create an order ID for the file in order to order it. And then the last step enables us to also download the data. And you can follow this notebook, and basically what it does is that it will store a file from which consists the CAMS global reanalysis data in the data folder. And with this data, we now go on to the notebook 11, which basically showcases you how you can load the data, how the data is structured, how you can visualize it for one specific time step, and then also how you can animate the data over the 31 consecutive days in March in order to really see the development of the ozone hole last year that appeared on the Arctic. So as I said, yes, we focus on the CAMS global reanalysis data. We again start with loading some required libraries, and we also make use of some predefined functions. And this is the same concept that is used as I showed you with the HDA API functions, but it's a different set of functions. So, but this notebook is also available for you, which you can have a look. So if we open this notebook, you also see a set of different functions which help you to load and also reshape some data, and also to visualize the data. We will not make use of all the data, because this is a set of functions that is applicable for a wider training on atmospheric composition, but we will make use of some of the functions in this notebook. And again, here with executing this cell, we load all the functions. And if you new to this concept also, and if you want to get more familiar with the functions, what I can recommend you is that for any function we apply or we make use of, you could also enter question mark and then the name of the function. And one function we will make use of is, for example, visualize P color mesh. And if you enter question mark and then the name of the function, so visualize P color mesh, and we execute it, then the doc string, so the description of the function is opened. And this might be quite helpful for you in order to familiarize yourself with the function, so you see which keyword arguments are required and also what a function is doing. And so the first step is to load the data. The data is, so we requested the data in netcdf format, and so we define the path to the folder where our data is stored. We have a netcdf format, and with netcdf we can make use of xarray, which is a very flexible and powerful library in Python that makes it very easy to handle and also manipulate multi-dimensional data, and also specifically data that are stored in netcdf. And so there is a function that is called open_dataset. And with this function, we can load one netcdf file. And this is what we do here. So we execute the cell, and as a result, we get an X-array data set. And the data set is can combine more than one variable. So it's like a combination of different variables. But in our case, because we only requested one variable, we have here now a data set with one variable and a set of coordinates and dimensions. And because it is model data, it is very regular in a very regular format, and we have latitude and longitude information, and then 62 time steps. So for 2 times for each of the days in March 2020, we have atmospheric the ozone information. And so the next step is then, so because we have a data set, but we don't have access to the real data array information and the data itself. So the next step is to extract out of our data set the variable we are interested in. And this is what we do here. We can extract a data array out of a data set by indicating the name of the variable, which in our case is GTCO3, and we put this in square brackets. And the result is then that we extracted a data array. So we have the data array of total column ozone information. It has the same dimensions as our data set, but now we also have more additional information specifically to our data variable. So we have also a set of attributes which describe our data in a more informed way. And so we see that the total column ozone information are disseminated in the unit kilogram per square meters. And we have a title or the long name. So we also know what the variable is about, and also the standard name. And so what also Antje showed you in her plots, that a common way is to represent total column ozone information in Dobson unit instead of kilogram per square meters. And for this reason, the next step is to convert our loaded column, total column ozone information from kilograms per square meters to Dobson units. And by dividing the data values with this factor here, we can easily convert the total column ozone data from kilograms per square meters to Dobson unit. And if we do this, then we still have our data array, but now we converted the values into Dobson unit. And now we are in a much better state to also represent the data and visualize the data in Dobson unit. And this is also the next step. So we actually already, because now we have our 3-dimensional array, so time and latitude and longitude in Dobson unit, and now we can visualize the data. And let's now visualize it for one specific time step. So we have 62 time steps, if I remember correctly, exactly. And so we can visualize it and we can make use of the function visualize_p color mesh. And this function it combines the function p color mesh from matplotlib and a very powerful visualization library called CartoPy, which is also available for Python, because CartoPy allows you also to visualize the data in different projections. And specifically for our use case, this is great because we can just visualize the data with a focus on the Arctic. And for this, we can specify orthographic projection, and we can just say, so please focus on the Arctic, for our visualization. And so the function takes a set of keyword arguments. So we see here that we use our data array, and because our data is three-dimensional, we focus on one specific time step, and we can here indicate a specific index for our time step. We also have latitude and longitude information, which is from our data array we loaded. Then we specify the projection, which I already said for our use case. The orthographic projection is very good in order to focus on the Arctic. We can define a specific color scale, and this is also something where you can play around with. So feel free also to specify a different color scale. We can define the unit and also the title of our plot. And here we make use of the long name information, which came with our data file. But additionally, we also add time and date information to our title, because this allows us also to know for when the data is valid. And we specify minimum and maximum ranges of our color scale in order to visualize the data effectively. And so we can execute a cell, and then we see, for example, here for the 21st of March at 0 UTC, we see already the ozone hole, so like drops of the ozone to values around 150 Dobson units. And here, this is also what you can play around with. If you look at an earlier day, like let's say at the 2nd, so at the 2nd March at 0 UTC, we see that the ozone hole has not been developed as strongly as it was on the 21st of March. And the last step is to animate now over the total column ozone information over the period of 31 days. And for this we define a animation function, which consists in principle of 4 parts. So the first part is again making use of the visualize p color mesh function. And this is setting our initial state. And this is basically, we set the first index, which is 1st of March at 0 UTC. And we set here the same parameters as we had in this plot before. And here we set the initial state of our animation. Then we define the number of frames we want to animate over. And because we have 62 time steps, we also set the number of frames to 62, because we want to go over all the time information we have available. And then we define a set of functions with which we can then combine in order to animate our plot and our visualization. And so one function is the draw function, and this is also using so this is basically the function is saying, so for each of the time steps, please update the visualization on our plot with this information. And so important is here that we here choose not a specific number for the index, but an index that can be updated. And we also want to update the title and the date or the day information during the animation. And then we have a function which initiates the animation, and this is basically where we just say, okay, with the initiation, please return our initial plot. And with the animation function, we want to continuously update our draw function, which updates our plot and visualization. And then we can combine everything in the in an animation function, which is also a function from Python. We can set a specific interval, and we can also say that if we went through all the time steps available, then please also repeat again and start again on the first day. And then we can execute this. If you execute the cell, it can take a bit, because it just has to load 62 time frames and visualization plots, but it will execute eventually. And then the next step is that we can play this animation as a video. And you see here that basically we see now the evolution of the total column of ozone in March 2020 over every 12 hours over all the days in March. And it's a very nice animation where you see also how the ozone hole has developed. And with this, I would end my presentation and my demonstration, and I would go back to Anne-Kathrin. Thank you.
Thank you very much, Julia, for the demonstration. It was very interesting. So it's 12 o'clock, right on time. We will go to the Q&A in just a second. I just want to whet your appetite for any of the next webinars that we are organizing, because this is the 8th in a series of 12 webinars on the Wikio DS that we have been organizing, and the first one on the expert thematic webinars. Which, today is about atmosphere applications, but if you have an interest in land applications, marine applications, please do register for the upcoming webinars in June and then September. You will receive automatically an invitation for the next webinar as you've registered for this event. And we hope to see you all there. Don't go yet, because we will start now with the Q&A. I've seen a lot of questions in the chat. A lot of them have already been answered in the chat itself, but for those of you who haven't seen it, the first question is, why is a polar vortex not such a problem in the southern hemisphere? I believe Antje has just left, so I'll read her answers. So the polar vortex is much stronger and less perturbed in the southern hemisphere because there's more land surface and mountains in the northern hemisphere that cause more disturbances to the atmospheric circulation. And that's why we see ozone holes in the southern hemisphere on a regular basis, but not in the northern hemisphere. Can we directly import and use these greenhouse gas flux datasets in Jupyter Lab as shown earlier? I believe the question goes to Julia, perhaps? Oh, she's...
I had rights to
okay.
access. So to be honest, so all the data that you can load, I'm not, let me just check if the greenhouse gas data is also available. But what I showed you basically before is, so you can go to Wikio and then data, and then you can see like all the data sets that is available. But I guess the greenhouse gases, yes, are available. So you should be able to, if you follow the notebook and also the example I showcased you, how you can retrieve also a API request, you should also be able to load the greenhouse gas flux data set directly to the Jupyter.
Okay, thank you. Could you give me some information regarding error covariance of CHEMS forecast for temperature, WV, and ozone profile? Mark, but is Mark still here? Okay. Well, let's see in the chat what the answer to the question was. I don't think so. Perhaps as we don't have Mark here anymore, this is a question that we can answer later on in the through the okay, I'm here. Anna Maria, can you make Mark a speaker? Perhaps I also saw one question earlier on if the presentation slides will be made available. So yes, this webinar is being recorded and it will be uploaded on YouTube. So you will get the link to that later after this after the webinar ends. Oh, hi, Mark. Hello.
Hi. So for this question, I think Antje is the expert on the data assimilation, but so I would recommend for Prajwal to contact Copernicus support at ECMWF, and that we can answer that question. The information will be there. It may be there somewhere on the website, but it's best to, for a specific question, send it to Copernicus support.
Okay, thank you.
I just had a comment, if you don't mind, Anne-Catherine,
yeah, sure.
about the first question about the polar vortex. I think just to make clear, I mean, this is the way atmospheric dynamics work because of the rotation of the planet and the heat differential between the pole and the equator. This sets up these jet streams, and of which the polar vortex is one. Over the southern hemisphere, you've only got the Southern Ocean, so there's nothing to perturb it like there is in the northern hemisphere, and so this is a persistent feature every year. It's not really a problem. It's a feature of atmospheric dynamics.
Okay. And
then the ozone depletion occurs within it. But as Antje explained in her talk and in the answer, northern hemisphere has a lot of mountains and topography, and so you don't get such a persistent flow in the lower stratosphere, and so you don't see it as frequently.
Okay, good to know. Thank you very much. I think most of the other questions have been answered in the chat. So if there are now any questions left, please don't hesitate to reach out to us at support@wikio.eu or Copernicus support at ecmwf.int for the excuse me, the Copernicus Atmosphere Monitoring Service related questions. And we thank you all so much, all of the speakers today, to give their insights and their demonstration in the use of atmosphere applications in Wikio, and all of the participants to stay until the end and participate so interactively with the webinar. And we hope to see you next time. Bye.